We're going to calculate the concentration of the free metal cation from the formation constant. In this example, the mercury complex is formed from a solution that contains 0.001 molar of mercury nitrate and 0.8 molar of ammonia. Calculate the concentration of the metal cation, and they've given us the formation constant. Since they've given us the formation constant, my equilibrium should reflect the formation of this complex. So I'm going to take a look at this complex, and I see that there is 1 unit of mercury and 4 units of ammonia. And in the context of these type of problems, ammonia would be aqueous. I also like to write down my given, which is my Kf. You want to make sure that this equation is balanced by atoms and by charges. The next thing I want to do is set up my ice table. Initially, I have 0.001 molar of mercury, 0.8 molar of ammonia, and initially I have no complex. For the change, it is plus or minus the coefficient times x, and by convention, minus on the reactants, plus on the products. So this is going to be minus x, minus 4x, and plus x. For equilibrium, it is initial plus change. All right, now I have my ice table and I examine it. I see that I have 2 reactants. Like in General Chem 1, when you see 2 reactants, you do have to stop and determine the limiting reactant. The limiting reactant is just converting the reactant to the same product. And for these type of problems, we can assume that there's 1 liter just to make our math easier. I take a look at my balanced equation. For every 1 mole of the mercury cation, I have 1 mole of the complex. I'm going to convert the ammonia. Take a look at my balanced equation. For every 4 moles of ammonia, I have 1 mole of the complex. When I compare answers, I see that the mercury cation gave me the smallest amount of product. Therefore, mercury cation is my limiting reactant, and I can say that X equals to 0.0010. Now I'm going to come back to my ice table and clean up my ice table. That means at equilibrium, I can go ahead and solve for some of these numbers. Now mercury is my limiting reactant, and under other conditions, that means that it would be consumed at equilibrium. That would equal to 0. But this is an equilibrium, and the formation constant is a very high number. So we can assume this goes to completion, but nonetheless, there's going to be a little bit left of that mercury. So we're going to come back and maybe form some of that mercury. So we're not going to call that 0. We are going to have to call that X. But for ammonia, we can go ahead and solve for it. 0.8 minus 4 times 0.0010, and this gives me 0.796. And for the complex, we can call that 0.001. All right, we got all that we need. We have our ice table. We determined our limiting reactant. Our limiting reactant will allow us to solve for equilibrium concentrations. The next thing we want to do is set up our formation constant expression. So remember that Kf is equal to the products over the reactants raised to the power of their coefficients. I'm going to go ahead and plug in the numbers I do know. I'm going to clean this up a little bit. And I'm going to solve for x. Solving for x means I've solved for the concentration of mercury, and this equals to 1.3 times 10 to the negative 22 molar. Let's take a look at another example. In this example, the iron complex is formed from a solution that initially contains 0.006 molar of iron nitrate and 0.1 molar of sodium cyanide. We're asked to calculate the concentration of the metal cation, and they've given us the formation constant. The first thing I want to do is come up with a balanced chemical equation. I also want to write down my formation constant. I also want to make sure that my equation is balanced by atoms and by charge. Once I know that I have a chemical equation that's balanced, I can go ahead and set up my ice table. Initial, change, equilibrium. Initially, I have 0.06 molar of the iron 2 plus. I have 0.1 molar of the cyanide, and I have 0 of the complex. For my change, it's going to be minus x, minus 6x, and then plus x. Don't forget that coefficient for cyanide. For equilibrium, it's initial plus change. We have two reactants, so we're going to have to stop and determine the limiting reactant. You can do this in your head at this point, or you can go ahead and show your work. So for every 1 mole of iron 2 plus, I have 1 mole of the complex. And do the same thing with the other reactant. Take a look at the balanced equation, and I see for every 6 moles of Cn minus, I have 1 mole of the complex. And this would give me So I'm going to examine. I see that 0.006 is a much smaller number. So therefore, iron 2 plus is my limiting reactant, and X equals 0.006. Now that I know what X is, I can come back to my ice table and solve for the equilibrium constants, equilibrium concentrations. The iron 2 plus technically is the limiting reactant, but we can't assume that we go to complete 0. So we're going to have to call that X. Cn minus, we do have X, so we can go ahead and solve for that. 0.1 minus 6 times 0.006, and that's going to give me 0.064. And for the complex, we have X, and that's going to equal to 0.006. All right, we have our equilibrium concentrations. We can go ahead and set up our Kf expression. Remember, that is products over reactants raised to the power of their coefficients. I'm going to go ahead and plug in the numbers. And don't forget to raise that to the power of 6. I'm going to clean that up a little bit. And I'm going to solve for X. Remember that X is just the concentration of iron 2 plus. So X equals 8.7 times 10 to the negative 31 molar. Good luck and keep practicing.